Okay, so we can continue with the part two. Think I've changed the recording setup a bit. Hopefully you'll be able to see more of the page now. And I've taken my face off of it because it seems to not work so well. Anyway, just to find a quotient ring. So now let's start giving some results about rings and ideals. So here's a proposition. It's 1.1.18, and it has 3 parts, and it says the following. 1, the kernel of a ring homomorphism is an ideal. 2, the image of a ring home is a subring. And 3, if phi is a ring homomorphism, then there is a ring isomorphism which goes from R modulo the kernel, so it's the quotient ring. The kernel is an ideal, so I can quotient out my ring by this ideal. And this is isomorphic, so I'm writing this as an arrow to the image of phi. So this is a ring, this is a quotient ring, and it's isomorphic to this ring, which is a subring of the ring where the map goes to. Great. So this is basically like sometimes called it the first isomorphism theorem for rings or something. You should have seen this. If you haven't seen this in an exercise, prove this. We'll just use it over and over again, but you can try improving this if you want. Okay, so now let's continue a bit with some definition of some useful, more useful ideals through which we want to quotient out by and so on later on. So this is definition 1.1.20. So I'm going to let R be a ring, and P and M are ideals, and I want to assume that neither of which is the whole ring, so neither of which is ideal is 1. Then what do we have? 1, the ideal, this is again goth P, and this is goth M. My ideals are nothing but Gothic letters. Ideal P is called prime. If whenever you have a product of 2 elements inside of your ideal, then X is inside of this ideal, or Y is inside of the ideal, and 2, the ideal M is called maximal if there does not exist an ideal which contains it. So if there does not exist an ideal different from the whole ring, which is the ideal 1, so if there does not exist an ideal, say A different from 1, such that M is properly contained in A. In other words, properly contained, so M is not inside of A, which is some proper ideal of R, which is just ideal 1. So we can't find an ideal A that will fit in between my maximal ideal and R. So here are some basic examples. If you let P be a prime number, then the ideal generated by P in Z. This is both. It's both prime and maximal. And so here's a proposition about these maximal and prime ideals. So 1.1.22. You've probably seen this before. Every maximal ideal is prime. Two, if I let R be a ring, then P is a prime ideal if and only if. So, if and only if R mod P is an integral domain. Similarly, M is maximal if and only if R modulo M is a field. So in this case, this example that we had up here, when you Z mod PZ is an integral domain, but it's also a field because F is the same as FP. 3. The only prime ideal in a field is the zero ideal. Later on when we're talking about ideals, we're almost always going to ignore the zero ideal. But okay, that's the third condition. Fourth, if phi is a non-zero ring homomorphism, then curve phi is a proper ideal. By which I mean, i.e., curve phi is contained, but it's not the whole ring R. Now I'll need to write that. So curve phi is not the whole ring. 5. Every proper ideal is contained in some maximal ideal. Great. Again, I'm not going to prove this. This should be, you should have seen this before, hopefully. If not, then trust me or go away and try and prove it. Okay, so we have a bunch of ideals. We know what it means to be prime and maximal. Now let's start doing operations on those ideals. So let's start adding them and multiplying them. So here's a definition. So if you're wondering where the number theory parts are going to come in, it's going to come in later. But at the moment, I'm just trying to get you all up to speed with ideals and what you can do with them, because somehow I'll tell you what we're going to do with ideals, and then we're going to actually study this in specific examples. So I'm going to let A and B be ideals in a ring. In a ring R. Then we let the following. So I'm going to write A times B. This be the ideal generated by product of elements in A and B. So as a set, this is you have sums of, say, AI, BI, say some finite sums I equals 1 to k, say, such that AI and B. AI is in A, BI is in B. This k doesn't have to be fixed. It can be any finite number. So any positive integer will work. But you just don't you don't want to allow an infinite sum. That's what I'm saying. So as a set, this is what the ideal looks like. 2. I'm going to let the ideal A plus B be the ideal generated by sums of elements in A and B, i.e., as a set, this looks like you have like x times A plus y times B, such that x and y are elements of R, A is in A, and B is in B. As a set, this is what it looks like, and you can check that this is, again, an ideal. 3, so this is how I've defined my addition of ideals and my multiplication. If A plus B, this ideal that these two ideals generate is R, which is the same thing as the ideal generated by 1, if we're in this situation, we say A and B are coprime. You will see later comparing this to the usual notion of coprimality for like numbers. So when we say like 2 integers are coprime or something, this is just a generalization of that in the language of ideals. Just say we write A divides B if there exists an ideal C such that B equals A times C. This is my multiplication of ideals, as I've defined in part 1. Okay, so this concludes our recap on rings, and next one we'll start talking about irreducible polynomials and so on.